We're now going to look at a couple of modeling problems. The day that we did this class coincidentally happened to be January 21st, which I believe is statistically the coldest day of winter, midwinter, the day when we're most likely to get the coldest temperatures. The temperature on class day was in the mid-60s. This is 2 days later, and I woke up this morning early before sunrise. There's a strong wind blowing and it was entirely comfortable outside. The temperature is about 65. I think the low temperature last night was about 62 or 63. Very unusual for this time of the year. In any case, the model that we want to make is a model of the average daily temperature in Fahrenheit degrees versus the clock time T, and you can't see it, but it's in days since January 1st. So we start the clock, or we start the graph here on January 1st. We're given the information that the average temperature is 35 Fahrenheit on January 21st, and that's the minimum. And we're going to make an assumption here. I'm not sure this is really true, but the average high temperature is the highest daily average temperature is 75 degrees. We're going to just say that's on July 21st, and that's our maximum, and that's probably not far wrong. We want to model the temperature. Now it's clear that the temperature starts pretty low on January 1st, reaches a maximum in the summer, comes back to its low point 365 days later. How are we going to do a circular model to understand this graph? Well, we start by drawing a circle. Now that circle has to represent the fluctuation from minimum to maximum temperature. The minimum temperature, remember, is 35, so that the bottom of this circle should be at 35, at average daily temperature of 35. The top should be at 75. That means the middle is going to be halfway between, or at 55, and we see that we put the average daily temperature at 55 Fahrenheit along this line segment, dotted line, that's centered at the center of the circle. The circle is going to have a radius of 20. Since it goes from 35 to 70, which is a difference of 40, the diameter's got to be 40, so the radius is half of that, or 20. Okay? Now, if we start at the usual starting point for a sine function and go around the circle, we're going to get the graph that you can just barely see here. It's in a light dotted line, and that's a graph of our standard sine function, and it's clear that that's not the graph that we want to model temperature. Temperature doesn't start going up on January 1st and reach a maximum around April 1st, then go back down to a minimum sometime in October. That doesn't make any sense. But we do have the right shape of the graph, and if we could take this graph and shift it to the left so that the minimum point of the standard sine function meets the minimum point of the graph that we expect for the temperature, then we would have what we want. Well, we can easily do that. We just have to figure how far we have to shift this low point to get over here. Then we just shift the whole graph that far. Now, the low point on the standard sine function on a 365-day cycle occurs at 3/4 a cycle. The first quarter we go from 0 to maximum, then back to 0 and down to minimum, then back to 0. When we hit this minimum, we've gone through 3/4 of the cycle. 3/4 of 365 is 273.75. So at day 273.75, the standard sine function is at its minimum. We shift the standard sine function over to where the minimum occurs on day 21, which is January 21st. That involves a shift of, well, from 273.75 to 21. We have to shift left by 252.75 days. That's easy to figure. Just subtract the two numbers. So we have this shift of our standard sine function graph, and that's a horizontal shift, and we're going to use that in setting up our model. Now we have just about everything we need to do our model, believe it or not, and we'll see how this all comes together in a minute. The only other thing we need is the angular frequency with which we have to move around the circle. Now, we're going to start so that we start at this point moving downward, which means our starting point in the circle is going to be here, but that's not going to affect what our angular velocity is. The angular velocity is going to be such that we cover the 2 pi radians of the circle in 365 days. So it's going to be 2 pi over the period, or 2 pi over 365 days. That's going to be our angular frequency. So we can kind of summarize what we know. Here's our angular frequency. We center the circle. The circle has a radius of 20. We center it at an average temperature of 55, and we shift the standard sine function graph to the left by 251.75. That gives us the following model. As you should have noted in your text, our model is going to be a sine function model. A times the sine of omega times the quantity t minus c plus d. Now your book uses b here instead of omega, and that's not a bad idea because omega is not real general and b is pretty general. But in this case I want to use omega because we're used to omega from the activities we did last week, from our viewing of the graphs and so forth. A is going to be the radius of the circle, which is 20, because of course that's going to give us the amplitude. Omega is the angular frequency, 2 pi over 365. C is our horizontal shift. By subtracting the horizontal shift from t, that accomplishes the horizontal shift that we want, and you should understand that from first semester. And d is our vertical shift, which is the height to which we raise the center of the circle. Since the center of the circle is at 0 for a standard sine function, then when we shift it up to y equals 55, we vertically shifted it by d. Now our model, now we just write out our model. We just plug in the values of the parameters into the model, and we get the specific model. And I don't think I have the whole model here, so let's see, we've got to get to 55 in the end. Okay, so here's our model corresponding to the circular model of annual temperatures in this location.